In this video, we're going to be introduced to capacitance. So a capacitor is two conductors separated by an insulator. So notice we continue to discuss conductors and insulators. And so we're going to bring the principles from Unit 1 into Unit 2. So we defined capacitance as the ratio of the charge on one of the plates of the capacitors divided by the potential between the capacitor. So that's a coulomb per volt or a farad. But we have to be very careful that is a ratio of charge on the plates to the potential. So if you hook up your capacitor to a different power supply, you're going to get a different amount of charge on the capacitor. It's just that the ratio of the charge to the potential, or the potential difference I should say, equals the capacitance. The capacitance is really the measure of the capacitor's ability to store energy. So it tells you how much energy you can store in that capacitor. So based upon how much potential you put across it, how much charge is going to move between. So how much work actually has to be done against the electric force in order to charge the capacitor. Now we do have to be careful in how we think about the charges moving in a capacitor. The charge never actually moves in between the plates, so there's never any electrons actually flowing in between the plates. What actually ends up happening is there is charge sent from the power supply, so electrons. We'll talk about current in the next topic. So there's actually a flow of electrons, and those electrons sit on one plate. And now we have what was once a neutral plate and one that is negative now. And the electric force caused by the fact that now there's a buildup of charge here generating an electric field is actually going to push electrons off of the other plate and through the circuit. So what's happening is instead of electrons flowing from one plate to the other, there's a buildup of charge here which then pushes charge off of the other plate until you have a neutral set here. So one plate's going to be positively charged because it lost electrons, and one plate is going to be negative because it gained electrons. But it's the electric force due to this buildup of charge here that's actually going to push charges off of here through the circuit. Alright, so now we're going to explore how we actually can calculate capacitance. And that's going to depend upon the dimensions of the capacitor. So based upon the dimensions of your capacitor, you're going to find you can get a certain amount of charge on your plate based upon how much potential you put across between the plates. So I've drawn our parallel plate capacitor here, so this is why I keep emphasizing lines of charge whenever I'm talking about electric field configurations. And we're going to worry about the electric field in between the plates. In an ideal situation, the electric field is actually zero outside of the plates because they cancel each other out outside of the plates, and you only have a field flowing in between the two plates. So first I've drawn my Gaussian surface here, and because this is a conductor, the electric field along here is zero, and I only have electric field coming out of one surface of the Gaussian rectangular prism. So when I apply Gauss's law and I plug in for area, it's just A, or length times width. And then I can use my relationship to find the potential difference based upon the electric field. So I'm going to integrate between points A and B. So along DL, my DL would be between here. And since there is no dependence of the electric field along this path here, it simply becomes delta L. I can then rearrange this relationship to solve for the ratio of charge to potential difference, which we called capacitance before. And you notice it depends upon the electric constant. And so far we've been using the electric constant for vacuum, so we're going to continue to do that for a while. We'll discuss at the end of this topic what happens if there isn't vacuum between the plates, which is more what happens in reality. The area of the plate, and mind you, this is the area of just one plate, and then the distance between those two plates. And so in most traditional formulas, you see that represented with a lowercase d. So the capacitance that the capacitor actually can have is based upon the dimensions of the capacitor. Now I've just derived this formula specifically for a parallel plate capacitor. So two plates that are actually parallel to each other. If you have a configuration or a different shape of capacitor, so you can have cylindrical capacitors or spherical capacitors, you will have to go back to Gauss's law and use the appropriate electric field formula, integrate, and then make this substitution again. So I've done the derivation solely for a parallel plate capacitor.